Let's check out example number 1. It reads, two forces of 19 and 32 newtons. Now, we're not talking about the cookie, right? Or what some people like to call a cookie or a fig Newton. No, what we're talking about is an actual measurement. And you can probably guess where that measurement or who it was discovered by. That's right, Sir Isaac Newton. And so a lot of these things are labeled as newtons. Don't worry too much. We're not in a physics class. We're just learning some of the mathematics behind it. So one key thing that I want to make sure that you all remember is drawing these things out really helps you to visualize and see what you're dealing with. So when it says two forces of 19 and 32 newtons act on a point in the plane, I'm not going to get out a ruler and actually measure out 19 centimeters and 32 centimeters so that everything's exact. I'm just going to approximate that. But one thing I can approximate pretty well is next sentence says, if the angle between the forces is 118 degrees, find the magnitude of what we call the resultant vector. So the first one I will draw will be in red. And that one they said was going to be a length of 19 newtons. And again, acting on that same point that we started with, we are then going to draw 32 Newton force. And it's going to be an angle of 118 degrees between them. So I will approximate what that is and then draw this thing out. Now notice I drew it a lot longer because 32 is much longer than 19. So you see I have my angle with my two forces, 19 and 32, and I will draw in that angle of 118 degrees. However, if one force is acted upon that point in this direction of 32 newtons, and then the other, they said, was in that direction of 19 newtons, which sometimes I'll write that out. Others, we know that our resultant vector is going to be measured in the same. Well, then what do I need to try and find? Well, what did they ask us to find? The magnitude of the resultant vector. So I know it's going to be drawn somewhere in between the blue and the red vectors, probably more towards the blue because it was the force that was greater, but I want to know exactly where. So what I'm going to do is I'm going to start by drawing out that red 19 Newton vector all the way up here. I'm just going to move it up that blue vector, and right at this point, I'm then going to draw it the same direction and hopefully the same length. Then I'm going to do the exact same thing, but this time I'm going to do it along this red one. And I'm going to draw and just take this blue one here, and I'm going to slide it over here so that it connects with this side. And hopefully you'll notice what shape will take place. That's right, our parallelogram, which now allows me to draw from that point in question here, that thing they call the resultant vector. Now, of course, we're trying to find the magnitude or the size or the length of that thing. So call it X, call it whatever you want. But remember, even though we came up with two different triangles, I'm going to just pick one. And I'm going to pick the one on the right here because I have more room to work. And I know that this blue vector here is the exact same as the one to the left in blue. So when I have this, hopefully you notice I have two sides. But remember that one angle of 118 degrees that they gave me was cut. And it definitely was not cut evenly. Even though some of your drawings may appear that way, remember one of our things was a force of or length of 32, and the other vector was 19. So there's no way that a 32 and 19, when I draw the resultant, is going to be right down the middle. And you can probably guess when it would be, but I'll get to that a little bit later. So what we're going to have to do is try to utilize the fact that we know, we just reviewed it, that because this is 118 degrees here in this angle, how can I find either this adjacent one or this adjacent one? Well, hopefully you remember we talked about it. If I was to extend out this side or this side, we know that this angle and that 118-degree angle would be supplementary. That's right. So again, if this is the same as that because of alternate interior angles, because of that transversal that is cutting those two parallel lines, then we know 180 minus 118 would give us 62 degrees. And so therefore I know not only is this 62 degrees, but so is this. And hopefully you recognize what kind of formula we're going to have to utilize in order to find that value of x now. Because we have a side, an included angle, and a side. That's right. We're going to get sassy, and we're going to use our law of cosines. Now, again, if you need to label all of these things with A, B, and C so that you remember what the formula is, that's fine. But I know that the included angle is always opposite the side that I want. It's going to be my length squared equals those other two lengths squared and added together minus 2 times those lengths times the cosine of our included angle. And so very quickly filling all of these in and then working all of this out, don't forget you're going to have to take the square root of both sides in order to find what your x length would be, which by the way is called the magnitude of this resultant vector. So very quickly, I'll work this out in my calculator and then make sure that everyone gets the right answer. All right, so not too bad. Hopefully we're just seeing that we're utilizing our law of cosines, but again, the hardest part on any word problem is setting it up. And hopefully you can see that the drawing definitely helps you to visualize what you're dealing with so that you can recognize the law of cosines is what you had to use in order to solve. Let's talk about a force of 18.0. Now, again, you might be wondering, why would they give us 0.0? Well, look at the other one, 74.0. So how many sig figs are we talking about now? Good. Hopefully you said 3. We want to know a force of 18 pounds, and they're telling us now, a force of 18 pounds is required to hold a 74-pound crate on a ramp. What angle does the ramp make with the horizontal? So again, I wanted to give you one that resembles the one we just did, but changes up what's given and what's being asked. So first things first, let's draw it out. Let's draw our horizontal. Let's draw our ramp. And then with that, we're going to have some point on there that they are going to have, in this case, a crate. So again, I'll use C for a crate, B for box, whatever you want. And it's on our ramp. And then it says a force of 18 pounds is required to hold a 74-pound crate. So we know what's going to be at play here is going straight down. We will have that 74-pound crate going straight down gravity with Earth. Then it said an 18-point force is required to hold that. So we know that there's going to be a force of gravity pulling it downwards, right? Then there's also going to be that one pulling it up the ramp. And so that this time is 18 pounds. Now, again, if I took that and just slid it down this, I could go ahead and draw that one more time in the same direction and the same length of 18 pounds. Notice I already have started a parallelogram. If I drew that other one that is here and just shifted it over, I'd have my parallelogram, and then I could draw my resultant vector, which is the one that's being played on the hill that we talked about. But in this case, I don't care about that, so I will just draw it in so that I have my or another right triangle. So with all of this, we're going to have to then take and find what they wanted us to find, and that was the angle that the ramp makes with the horizontal. So we are looking for that angle theta. So how are we going to do that? Well, hopefully you notice the one thing that we definitely do have is the fact that if this is angle theta, I'll call this alpha. And we already know that this is a 90. And so if this is alpha, then we know that this is also theta because these three angles added up gives me 180. And then these three angles in this triangle add up to 180. And since we have one that's a 90, one that we're calling theta, and one that's alpha, we know that those three things add up to be 180. Well, then so do these. And if we fill this in over here, we can also call that alpha. Now keep in mind what we're trying to find is what we called theta. And so what types of things are we going to use in order to find those? Well, since we have a right triangle going on right here or right there, I can use the side lengths that I know. And one of them they gave us from the beginning was 74 pound in this case crate, and then that 18 pound force that held on that ramp, that crate. And so since I know those two sides, I can use what trig function in order to find it for theta. Well, hopefully you notice that it is the opposite over the hypotenuse. So we would this time be utilizing sine. And sine of that angle theta would be opposite over hypotenuse. I'm not going to keep including the 0.0. And with that, we now have what we need in order to solve, but we just have to make sure that we do the inverse in order to reverse our input and output. So we will do inverse or arc sine of 18 over 74, and that will equal our angle theta. And once you plug that into your calculator, remember, hopefully you found it. They wanted 3 sig figs because they gave us 3 in each. So you should have got an answer of 14.1 degrees. So not too bad. I tried to go very slow on the previous example because I know all of this is new and how we're drawing it out. But if you can draw this out and kind of follow some geometry and using the sum of triangles along with the sum of a straight angle that we had here, along with this, and labeling everything correctly, not much work to this one compared to the last. So here's our 5th and final example. And of course, I saved the best for last, didn't I? Here is one of those types that has bearings, where we're out at sea and we don't really have a McDonald's or Taco Bell to say, take a right or left at. All we have are blue horizons. So in this case, we have to use a compass. And remember, there's a couple different ways that they can give that to us. Either way of bearings, an angle between 0 and 360, which remember we always start north and move clockwise. Or we can use look north, look south, and then rotate east or west, some acute angle. So in this case, you can hopefully see they did not give us a north, south, east, or west direction. So they just told us 25. So reading this whole thing first says a ship leaves port on a bearing of 25 degrees and travels 61.4 kilometers. The ship then turns due east and travels 84.6 kilometers. How far is the ship from port, and what is its bearing from port? I'm going to highlight one key word that a lot of people mix up. Be careful with the from. Okay, from port means you're looking from there, not to there. So let's draw this out to the best of our ability and try to utilize all of our previous knowledge to then answer those two questions. So first things first, it said that a ship leaves port on a bearing of 25 degrees. So I'm going to label this point right here as my port, and I know that it is traveling 25 degrees. So I'm going to start by looking north and rotating clockwise 25 degrees. So that would be that little angle there. Okay. Now, if I wanted to put the east line, I know that those two angles would be complementary, and therefore 90 minus 25 would be 65 degrees. If I wanted to include that, I don't know if I'm going to need it, but hey, since I know it, I might as well put it. Okay. Now, that distance, that length, they said was 61.4 kilometers. So I can also put that length there. It says then the ship turns due east. So from that point, I will use a different color. It then changes and heads east. And this time it heads east a little bit longer than the other one. It's 84.6 kilometers. And I don't need my bearings on this one because I know it was due exactly east. But what I can do is, since this line right here is parallel to this line right here, then this line is what is called a transversal. And if I drew this 25-degree angle there, then what should we know? Alternate interior angles, this would be 25 degrees. And obviously this would be 90, and that would be 90. So we have some more information that we might be able to utilize. Because what did they ask us to find? Two parts. So I'll label it A and B. Part A was how far is the ship from port, and part B, what is its bearing from port. So we had that port over here of P, and then this ultimately was where the ship ended up. So of course, what I'm going to do is connect those and draw to create my triangle. Now notice that 65 was cut, even though I thought I might need it, didn't end up coming into play. So don't let it try to affect you and say that the inside angle there is 65 degrees, because this whole thing to the horizontal was 65. So if you just want to flat out get rid of that, so hopefully you can see what you're going to have to utilize to first find how far is the ship from port. I will go ahead and label that as my part A. When I'm solving, that would be part from where we started the port to where we ended, if you want to call it E. All right, I need to find that distance. And because I knew that this side was 61.4, this side was 84.6, and because this angle and that angle are alternate interior angles, and this was 90, I actually have the angle included between those two sides. So I'm going to just add that up to get the total distance from there to there as 90 plus 25, which would be 115 degrees. And now that I have that, what should I be using in order to find x? And hopefully you said it, law of cosines. So again, x squared, my other two sides squared minus 2 times those things times the cosine of my included angle. Filling all that in, and then reminding myself to not forget to take the square root of that big answer. You know what the answer should probably come out, because it is the opposite, the hypotenuse, or the, the obtuse angle. Then we know that has to be longer than the longest side, which was 84.6. So taking the square root of that big old long mess, remember I advised you all to do this in your calculator from right to left, or just put an extra set of parentheses or bracket around it and punch it all in your calculator in order, and it should take care of it for you. Either way, you should have got your X answer, the distance from port to where it ended up as 124. Our measurement was in kilometers. And now that we have that, we can move on to part B, which part B asked us to find the bearing from port to where we ended. So we are trying to find the 25 degrees that we already have from north. We now need to also find that angle there. And in order to find that angle there, what are we going to have to use now? Hopefully you guessed it. Because we now have our good ratio of an opposite side and an opposite angle, we can now use to find this angle, I will call theta. In order to find that angle, I will use the opposite side, which is 84.6 in my law of sines. So I will use the sine of theta over its opposite side, which is 84.6, and that would be equal to the sine of 115 over its opposite side, which we just found to be 124 because of the 3 sig figs. Then going through and solving this, multiply over by the 84.6. And now we have the sine of theta by itself, but multiplying that out and getting some number, we will have to do our last step, and that is to take the inverse in order to reverse the order. So we will get the inverse sine of whatever that number is, that all of that comes out, is equal to our angle theta. But I must warn you, when you find your theta, after punching all of that in, and hopefully you got 38.3 degrees, that is not your answer. Don't get frustrated. Be careful. Make sure you finish. Remember, theta was just this. They wanted the bearing from north. So what do we have to do to that theta? We have to add 25 degrees to that to get 63.3 degrees would be our bearing. All right. So that's all I got for you. Hopefully you see that not much of this is new. It's just how we're utilizing our sines and cosine, our law of sines and cosines, in order to find all the parts or any of the parts that they ask. Number one key into doing any of these applications, drawing it correctly. All right. So be careful out there, both inside your house and outside. Inside with your math, outside with the world. That's all I got for you. You guys be well. Talk to you soon. Till the next one.